Mathematicians search for elegant algebraic structures that maintain an unbreakable symmetry, even when buried deep inside highly complex systems. This equation is a sixth degree, or sextic, polynomial. Specifically, it is the n equals 15 phase polynomial. While it appears dense, the coefficients reveal a mirrored architecture. The outermost edges show the pattern immediately. The leading coefficient is 233, matching the constant at the end. Moving one step inward, the coefficients for t to the fifth and t match at negative 2906. The next pair also reflects, both sitting at positive 699. The sequence converges on a central axis, the solitary 13,708 attached to the t-cubed term. In algebra, a structure with this mirrored property is called a self-reciprocal, or palindromic polynomial. This chart shows the 6 real roots of this specific polynomial, evaluated as decimals. They are arranged in 3 pairs. If you multiply any of these pairs together, the product is exactly 1. Every root in this polynomial occurs alongside its mathematical reciprocal. The mirrored coefficients and reciprocal roots are the direct consequence of the numerical sequence governing the equation structure. To understand why this polynomial behaves this way, we trace it back to its origin in wave mechanics and trigonometry. This equation represents a generalized trigonometric phase family, defined as E sub n of x. The coefficients in this wave equation are determined by sequential terms from the Fibonacci sequence. The variables f sub n minus 1, and f sub n minus 2 dictate the amplitude of each sine wave. By selecting an index of n equals 15, we plug the 15th, 14th, and 13th Fibonacci numbers into the structure. The variables become the weights 610, 377, and 233. The resulting algebraic palindrome is a translated map of overlapping sine waves, regulated by Fibonacci ratios. Converting a trigonometric wave equation into a solvable algebraic polynomial requires a bridge between transcendental functions and algebra. This formula defines the tangent half-angle substitution, which is a standard conversion tool that maps trigonometric inputs directly onto algebraic variables. Using this tool, we rewrite sine of x entirely in terms of the algebraic variable t. By applying a triple angle identity, the more complex sine of 3x also translates into a rational function of t. We then take these new t values and substitute them back into the n equals 15 Fibonacci phase equation. To clear the rational denominators, we multiply the entire structure by the term 1 plus t squared cubed. The equation organizes itself into the palindromic sextic. The symmetry observed in the coefficients is the geometric logic of the sine waves expressed in algebraic form. The tangent half-angle substitution ensures the underlying geometry of the waves is preserved. That geometry is baked directly into the mirrored coefficients of the final polynomial. Solving a sixth-degree polynomial directly is a major computational challenge. It is often mathematically impossible without a structural shortcut. Because this polynomial is symmetric, we can divide the entire equation by t cubed to balance the powers across the center. This division allows us to group matching symmetric terms together, combining positive and negative exponents. This equation defines the trace variable, u, as the sum of t and its reciprocal. By substituting u back into the grouped equation, the quadratic pairing collapses to u squared minus 2 and the cubic pairing to u cubed minus 3u. This compact equation is a solvable third-degree cubic. The complexity of the polynomial has been precisely cut in half. Solving this cubic for u generates a simple quadratic equation for t. Because the constant in that quadratic is always 1, the product of its roots is exactly 1. They are locked into reciprocal pairs. By isolating the trace variable, we use the polynomial's own symmetry to force the roots into reciprocal alignment. We've only examined the specific case where n equals 15. What happens to the cubic's roots as n scales toward infinity? Calculating the sum of all 6 roots of the original sextic, the value grows without bound. However, looking at the sum of the 3 trace roots reveals a perfectly stable pattern. This diagram shows Vietta's formula applied to the trace cubic. It proves the sum of those roots equals a precise ratio of Fibonacci numbers. Dividing this sum by 2 yields the half trace. By substituting the Fibonacci recurrence, where fn equals the sum of the 2 preceding terms, the expression simplifies to twice the ratio of sequential terms plus 3. As n grows larger, the ratio of sequential Fibonacci numbers approaches a permanent limit. It locks onto the golden ratio, phi. Substitute phi into the expression to find the final invariant value, exactly 4 plus the square root of 5. No matter how massive the polynomials grow, their macroscopic trace behavior is tethered to the golden ratio. In mathematics, there is a strict divide between a proven topological invariant and a numerical coincidence. This exact Binet formula calculates the remaining error. It algebraically proves how tightly the roots bind to 4 plus the square root of 5. Contrast this against the appendices of the source paper, which list shadows, close numerical approximations that lack a governing structural proof. A highly accurate number is meaningless without the algebraic scaffolding to support it. The exact invariant demonstrates truth, the numerical shadows merely hint at it. The value of the palindromic phase polynomial lies in how its symmetry allows rigorous substitutions to unmask the hidden infinite order within the equation.